So people, please let me know if the screen is visible.
Yeah.
Yes, ma'am.
Thanks. So, yeah. So this is actually a repetition of what we saw last week. So kind of a revision of what we went through last week. So I understand that yeah. So you have begun with some very basic introduction to do how to do image processing and all. So we'll go through. Oops, yeah. So we'll go through some of the problems that we have been talking about in the first week. So yeah, I'll request all of you to be on mute for this session, and whenever you have a question, please unmute yourself and ask the question. So let's begin. So okay. Why is this Yeah, okay. So the first topic that we'll talk about today is histogram equalization. So I think some of you have attended some of the previous sessions, live sessions, so and the classes too. So can anybody unmute and say why we need to do histogram equalization? Anybody? So I'm audible, right?
Yes, ma'am.
Okay, so
Used in contrast.
I'm sorry, I lost your voice.
It's used in improving the contrast of the image.
Yeah, it's kind of right. Basically, what happens, what I understand about histogram equalization is that so suppose you have a very skewed sort of image, either it has too many bright pixels or too many dark pixels. What you would want to do is in the histogram space, you would want to make the distribution of the image uniform. So the idea is to make all the pixel intensities that can be there in an image, you want to make them uniformly distributed. So that's the idea behind histogram equalization. And I suppose some of you have already gone through it about how to do it, but I'm going to go through it anyway. So, how do we do histogram equalization? So, first of all, the idea is that we want a image histogram where all the intensities have roughly equal values. So, yeah, sorry. Yeah, so how do we do that? We do that in this way. So, suppose we have an input image which is which we call I and has a dimension of m cross n, and all the image pixels lie in the pixel intensities lie in the range from 0 to 255. Okay, this is becoming, yeah. So now what we need to do is we need to transform this image in some sense such that what I said, the histogram becomes uniformly distributed in some sense. So now we have a image I, as I said, and suppose we want to keep the transformed image in this variable j. So j of ij will contain the transformed pixel at the position I comma j. So how do we do this? We basically, the operation that we perform is simply this, where what happens is that this is at position ij, right? So what you'll do is you'll find what was at position ij of the original image I, and you'll compute this quantity, which means what? This is basically probability. This p stands for probability and k stands for the pixel intensities. So what you'll do is, starting from 0, if pixel intensity 0 to whatever was there in I of I comma j, you sum those probabilities up. So this P of k, you can think of it as the PDF or PMF of I, and you sum them up from 0 to capital I of I comma j. So what that turns out effectively is, you all of you know, I'm assuming that this becomes the CDF of I, right? So you can write this as capital P of I of I comma j, because we are summing probabilities from the lowest value to some given value. So basically this becomes P of I comma j. So now what we are saying is, if we transform the image I, capital I, to something like this, capital J, which is defined by this, which means that capital J will contain the CDF of I, then we are saying that the histogram is equalized, right? So now let's try to look at how this happens. So let's think of it in the continuous space first, to be to be more clear. So let's forget that image pixels are basically discrete in nature, like this 0 to 255. Let's think of it in a continuous, from the continuous point of view. Why? Because it's easier to do the calculation that way, right? So now our pixels are all continuous values, and what we want to do is, what we want is that the distribution of j should be uniform in the continuous space. Okay, so yeah, so we want the pixel intensities of j to be uniform in the continuous space, which means what? That the CDF of j should be equal to this quantity. So suppose CDF of j is given by this Cj of x. What we want to, for j to be uniform, we have to ensure that this is equal to Cj of x is actually equal to x. So if you go back and compute what is the CDF of a uniform distribution, you'll see that this is what it turns out to be. So this quantity has to be ensured, that Cj of x is equal to x. Yeah. So what we do here is, so let's break up Cj of x. So Cj of x is what? It's the probability that j is less than equal to x. So this is how we break up the basically the cumulative distribution. So it's defined by this. So now, what is j of x? Yeah, so what is J? J, we have seen above that J is basically the CDF of I. So let's write J in that way. So let's replace J by P of I. Now what we do is, suppose we draw something like this. So this is basically given the pixel intensities, the CDF of that distribution, right? So in I. So suppose x is a value there. So x is basically what? This is what we want to find. So x is, so y axis here is the CDF and x axis here is the pixel intensities. So don't confuse this x with the x axis. So this is different. So now what we are saying is, suppose you have an image. So note that CDF is a increasing function. So not increasing, it's a monotonically non-decreasing function. So what happens there is, it starts from here and then it keeps on continuing to upwards until it reaches the value 1, right? So now what we do is, suppose we take the value x, suppose this is x, and from x we can find out what, where it strikes the curve. So from here we can see what is the value on the x-axis. Suppose this value is k, right? So what would that mean? Uh, what would that mean? That basically your PDF of, yeah, so basically this would mean that P of k equal to x, which means that the CDF of k is equal to x, right? So now let's do one thing, let's replace this x's value here. So here we had P of I less than equal to x. Let's think of this as P of I less than equal to P of k, as is written here, right? So now you see that this is a non-decreasing function, which means if we have P of I less than equal to P of k, we can also write I less than equal to k, because this is non-decreasing. Yeah. So now what is probability of I less than equal to k? What is probability of I less than equal to k? It is again basically asking about the CDF values. So this becomes capital P of k, which is basically the CDF value at for k. So that means, and now what is P of capital P of k? That is equal to x. So now you can put x here. So now what did you get? The CDF of j is equal to x, right? So this is what we wanted. And what we said in the beginning is that uniform distribution has uh, for that the CDF is actually equal to x. So CDF of x, CDF at x is equal to x. So basically, what did we prove here? That if you take a continuous setting, then by taking this kind of an approach where we set J to be the CDF of I, we showed that J turns out to be uniform, right? This is what we wanted. So now the problem is that we are not in a continuous setting. We are dealing with a discrete setup where images consist of discrete pixels whose values are from 0 to 255. But basically, these things are easier to process when you take up a continuous setting. So that is why when you come to the discrete setup, you just pick up this formula. You do nothing else. So basically, we approximate it in easiest terms. So what do? We take this in the discrete case also. We take this image j, and at position ij we compute this value. So these values are all computable from the image histogram, and you compute these values and you get the pixel intensity at location I comma j. So obviously this will not result in something that is totally uniform, totally well balanced in some sense, just like the continuous case. But at least we know that it will approximately serve our purpose. So yeah, so this is what is histogram equalization, where the motto was, what was the motto? That we wanted to kind of spread all the intensities equally. So there would be, we would like to approximately make sure that the intensities, the pixel intensities are more or less uniformly distributed on the histogram space. So how does that help? It makes rich use of the entire grayscale. So basically, you'll see that if you do something like this, your image is enhanced. So I is there any question at this point? Okay, good. So some examples to look at over here. So yeah, so you have an image like, hello, do you have a question? Who is this? Can you mute yourself, please? Thanks. So
Then someone say in chat like, please take example.
okay, okay. Okay, okay, thanks. Yeah. So examples, yeah, examples maybe in terms of maths we can work out later, but the it looks something like this here. So this is an image. You can see that you can get a basically an understanding of what's going on here, what we want to achieve here. So this is quite a dark image. It's not very visible to you. So if you draw the histogram of this, you'll see that the values are quite, in the darker range. So the pixel values. So this is the histogram. This is the histogram, and so the range begins from 0 to 255. See that all the pixel intensities are more or less distributed in this darker region. So that is what this image is. It's darker, right? So what we want to do is we want to not make it brighter, but we want to enhance the quality of this image. So how do we do that? So as I said that ideally in the continuous case, what we would expect is that this I mean, once you do histogram equalization, yeah. So once you do histogram equalization, you'll find that your image is enhanced like this. Okay. And so what happens is you take this distribution and you approximate it to something like this. where the pixel intensities now you can see instead of being 0 in this area, they are much more well balanced. Maybe they are not completely uniform, but they are much more well balanced. So that is the purpose behind histogram equalization. So yeah, I'll make sure to communicate to the other TAs to solve a real example for you in terms of taking a very small image and showing how it is. But yeah, so if you can all, what you can do is, since I don't have that example here, what you can do is you can take a what do you call it, a very small, say suppose 5 by 5 matrix, and fill it up with some random values from suppose 0 to 10, right? And uh, then you treat it as capital I, which is the input image, and then you try to find out what would be the histogram equalized image. Just go by this formula. So what is p of k? Small p of k, it's basically the probability of that particular pixel intensity k in the image. So what will it effectively amount to? This is basically how many times this pixel intensity k has come. Suppose k is 5. So in the image, in the 5 cross 5 image that I talked about, which consists of values from 0 to 10, how many times has 5 occurred, right? Divided by the total number of pixels in the image, which is m crossing, right? So basically inside the image you compute the probability of the individual pixel values. So now how do you compute this? You basically take this probability, compute this probability value first, and then you apply this formula. So at every position I comma j, you go to capital I, you find out what value is there, 5, 7, 2, whatever value is there. Suppose it's 2, right? So if the value is 2 at position I comma j of capital I, what you do is you take the summation, which means what? Small p of 0 plus small p of 1 plus small p of 2. So that will give you the final value, transformed value for your capital J at some position I comma j. So this is actually fairly easy to compute. So at this point we do not have a worked out example for this, but yeah, sorry. Yeah. So basically it tries to do something like this. So you can see for yourself that you are given a darker image, and by just doing this operation you can see how clearer the image has become, how enhanced the image has become, and that is through make transforming this distribution, which is where the frequencies lie in the lower range of the pixel scale. This has been distributed in a much more balanced way on the entire scale. So that is what more or less histogram equalization does. Just a little bit note on what happens when it I mean how, in what situations this won't work. So most of the times this is going to work. So there are a few limited situations when this won't work. So let's go through those examples very quickly. So what happens here? So this is an image of a lion, which you can see is very dark, right? And it has a histogram distribution of something like this. So suppose this value is what? This value looks like, suppose 7, right? So this so basically the pixel intensity 7 has a huge value and others have very very negligible values. So basically what we are trying to say here is that this image is consisting of pixels, that mostly consisting of pixels that whose value is 7. So let's not look into the solution. If anybody can tell me, I mean, why histogram equalization won't work here based on what we saw in the previous page. Anybody?
Pixel intensities are not much varying, that's why.
Okay,
Ma'am, probability will almost touch to 1.
correct.
Probability.
Right, right. CDF. You mean CDF, right?
I'm assuming in terms of probability right now.
So, see, what is happening here is that probability, yeah, you can think of that in that, yeah, it's more or less what you are thinking is on the correct line. So what will happen is, what do you want to do here? You want to take this image and you want to just find the CDF of it, right? So think in terms of
Right. Or
CDF.
in other terms, like you just said, ki the number of I mean, or for one pixel,
Hmm.
the intensity value is very high.
Correct.
Like that only we are going to calculate the probability,
Right,
right?
right. So
Right.
suppose, so since this value is too high, so what will happen to the, let's scroll back. Let's look at this particular CDF image. What will happen to the CDF is that for that pixel only, it will almost reach 1, right? So it will be very, very close to 1 because most of the probability mass is present here. Yeah, so most of the probabilities mass is present here. That is why the CDF will be 1 very quickly. So at this value, if you can compute the CDF, then it will almost touch 1. It will be somewhere around zero point 0.9. Suppose the other values beyond this pixel value 2, they contribute a little bit, suppose say zero point 0.1. So this CDF here is zero point 0.9 and the rest of it amount to zero point 0.1. So here basically you have an extremely high value. So what will happen is, wherever in this particular image, in the transformed image, wherever you have pixel 7, which is, remember, it's the majority pixel, there you'll have this high value of zero point 0.9, and there are very, very small number of pixels which other than this 7 pixel, which have value 1, and there are other very, very small number of pixels which are lower than 7, which will have value 0. So what would that mean is that in your so since you have a CDF value of zero point 0.9, what you'll do is you'll try to approximate this by doing a scaling. So you'll have to do zero point 0.9 into 255. So pardon me, today I don't have my tab, so I can't draw this for you. But yeah, so what will happen is that since you have a CDF value of zero point 0.9 for this pixel 7, so again going back, yeah, if you go back at this value, so whenever this I of capital I of ij is 7, capital J of ij will be zero point 0.9. So, and then what you'll do is to bring this zero point 0.9 into a scale from 0 to 255, you'll multiply zero point 0.9 by 255. So what will then happen is that it will be somewhere very high. So if you see here, it will be somewhere around here, somewhere around 200, something like that. So here there will be a very, very high value. So most of the pixels are 7 here, here in the original image. So everywhere you will have that zero point 0.9 into 255 value. So basically in your histogram there will be a very high value for this, and some other values will be there. So here you can see that again, since I mean, because of the logic of histogram equalization, this is not balanced. This is definitely not balanced, where you are moving most of the mass to one position, whereas the other positions hardly have any mass. So that is a problem drawback with histogram equalization. You can't work with intensities that are too skewed. So yeah, so that problem is always there. So this is one of the cases where histogram equalization kind of fails. So now that we have an understanding of histogram equalization, let's have a look at, I understand that you have gone through linear filters. So do you understand these things? I mean, what is a mean filter? Can anybody tell me what a mean filter does?
It will take mean of the pixel values.
Right. So can you, since you have an understanding of linear filters, can you tell me what a mean filter would look like? So suppose you have a 3 cross 3 filter like this, and you want to take the mean of, suppose, this first matrix, 3 cross 3 matrix. So tell me, I mean, if you can, what would be the values here?
All one.
Right. So if you do an all one, then these will be summed. So we want an average. So basically we have 9 positions. So this will be basically all ones, and there'll be a 1 by 9 outside. So basically, instead of all 1, it will be actually 1 by 9 at every position. Right? Did you get it?
Yeah, yeah.
Cool.
There will be 1 by 9 1.
1 by 9, yeah. So this is how whatever, so mean filter, one thing is that how mean filter, why do we use it, one application of it would be to smoothen out the image. So imagine at every location what you are doing is you are doing essentially an average of the pixel values that are around you. So essentially, if you do that, you'll see that at the end of the image, again, so yeah, at the end of this transformation, you'll see that all your pixel values have been smoothed out a little bit. So so that is one application of mean filter. So basically, linear filters are what that. Let's go through this. Yeah. So yeah, I think some of you saw this already. So this is what happens in a linear filter. So basically, you use linear combination of the coefficients present in the filter. So you do so it happens something like this as is pictorially shown here. So it's basically a convolution or a correlation procedure. And what you do is, so this is something that is very commonly used for different applications. Like I said, one is that you can make the image a little bit smoother. You can make it sharper. You can do lots of things with different types of filters, and this is how the filters are applied on different parts of the image. So um, yeah, I mean, what you do is you generally, if this is your image, you wrap this image with a layer of padding around it, so that you can take this 7 values, these corner 7 values, and then you do the padding, and then you apply the filters on the image, so that to make sure that your transformed image is of the same size. So this is more or less what a linear filter does. So
Madam,
yeah, go on.
but for padding, we generally use 0 or 1. Na? Here we have taken the upper row
Actually,
values
yeah,
only.
yeah, yeah. Actually, different. It kind of depends on the application. For example, if you think
Okay.
of, so this is a deep learning class at the end of the day. So you'll do CNNs here, convolutional neural networks. There you'll
Mm-hmm.
see that it's padded with zeros. So it kind of depends. I mean,
Okay.
what when you are padding with the same numbers, you are basically trying to imitate whatever was here in the padded
Okay.
region also. The idea is
Okay.
that you want this the convolution value for this central pixel. So that is why you need to do the padding. So if you don't do the padding, the problem that arises is that these this image, actually the size becomes lower and lower and lower. So you'll see during when you'll be taught CNNs and all, you'll see that mostly zero padding is preferred. So this is again very application based. So you can take a decision why what you want to use based on why you want to use it. So so these are kind of what we think of as filters. So let's something is very special about this filter. So there are some values which are there. I mean, it seems a little strange, but there is something very special about this filter. So can anybody tell me why? What what the special feature about this filter is?
The sum will be 1.
Some will be one. Okay, somebody is trying to join. Yeah, some will be one, that is fine, but alongside that, there is something special about this filter. So, what this does is basically, as I said, image sharpening is something that you can do through linear filters. So, this particular this particular filter is basically helping you in sharpening the image. Why? Because suppose um, suppose you take this 3 cross 3 matrix, right, and you want to do a convolution on top of it. Suppose your central location here is what do you call it, it's something, suppose 4, whatever is here, that's fine. And the so when you do convolution, what with this kind of a filter, what will happen, these four corners will be 0. We don't need to worry about them. All we need to worry about is the central pixel and the 4 pixels around it. So imagine if these 4 pixels around it are way different. Something like suppose very high value, suppose, or very suppose this 4, instead of 4, think of it as 100, and these are all ones, 4 ones. So then what will happen is that if you have a very different, so basically what you are trying to do is you have a central pixel, you are trying to look at your 4 neighbors. Are they very similar to you or are they very different? If they are very similar to you, then you don't need to do anything. It's fine. But if they are very different, then this value will turn out to be very large. Okay, so when you convolve with this kind of a filter, this central value will be very large because you have a -1 though. So the sign is different basically. So if your values on the neighborhood are very large, then this after the convolution, the value here basically the value here will be very large. So that is how sharpening happens. So basically this filter is a special one. So probably, I don't know, I'm not sure if this has been taught to you, but uh, there's a special filter called Laplacian, which actually is used for multiple purposes like image sharpening, edge finding, and so on. So I'll give you an example of what image sharpening looks like in a bit. So this filter that I showed you is basically a sum of this plus this. So what happens is Laplacian, when you use the Laplacian filter to basically calculate, how different is this the central pixel value from the neighboring pixel values. And normally what you do is you add whatever you find to the original, back to the original image, and that basically helps in um, what do we call it, in sharpening the image. So let's look at this. What does this filter do? It's very simple. So there's a 1 at the center. So again, let's look at the matrix. Suppose you have this, take this 3 cross 3 matrix and you apply this filter where everywhere it's 0 except here in the central position. So basically here in everywhere it will be 0 and 1 in the central position. So what will happen is basically if you convolve with this particular window, all the only value that you will get is 4. So at this position, at the corresponding position in the new transformed image, you will put the value 4. Similarly, if you take this window, then you will see that if again you have that kind of a filter with all zeros and 1 in the center pixel, you will get the value 3 and so on. So effectively what you will notice is at the end of the day, this kind of a filter uh, returns the image, returns the original image to you. So now what happens is, if so you have a Laplacian filter and you have an identity filter. And when you add them, you get this kind of a filter. And if you apply this filter on top of the original image, what you get is a sharpened image. Yeah. So what you get is basically a sharpened image. So this is how it looks like. So again, I mean, the bigger the value in the central pixel here, the better, the more the sharpness basically. So you can see here that these white areas, these edges are very blurry in this particular image. This is the original image, whereas these are all sharpened versions of the image. So you see that these areas are quite blurry. Okay, and let's compare with this image, which is basically transformed by this linear filter present over here, right? So what you'll see is that this these edges, if you see, if they while they look quite blurrier in the original image, they look a little bit sharper here. Similarly, if you use this particular filter, this image, this edge looks even more sharper. Right. So this is what we mean by sharpening, where you have these edges, these features are there, you want to enhance them. So you want to make them sharper. So this is what sharpening means, and obviously these sharpening these filters are there which are designed to do sharpening, and the value in this central location kind of tells you, how much sharpening you do. The more the value here, the more sharpening you are doing. So even here the edges are quite blurrier. if you look at these two images parallelly, you'll see that you'll feel like these edges are even these edges are blurrier. So uh, you'll see a much more sharper image here. So that is kind of what we mean by image sharpening, and obviously Laplacian filters are very popular in doing that. So yeah. So okay. So one thing, no cheating. Only the ones who are new to this in this session, tell me. So what you want to do here is that you have an original image, and you want to. This is an image of an eye. Suppose you want to shift the eye to the left a little bit. So what do you think would be a good filter for it? Anybody? And no cheating. So all you want to do is you have an eye at a particular position in this image, and you can see that this eye has shifted by a little bit to the left side. So there's a very very simple technique that you can apply using linear filters that will do this job. So yeah, let's go through it. So suppose you have this kind of a filter. Yeah, suppose you have this suppose you have this kind of a filter, which means what, that there's all zeros except a 1 in this position, right? So what will happen if you convolve this image with this kind of a filter? Again, let's go back to our example matrix that was given here. So what do we have? We have all zeros here. We have all zeros here and just a 1 in this position. So suppose again we take this matrix 3 by 3, and we want to see what happens with when such a filter is applied on this. So all are zeros here, all zeros, which means these two rows will be 0, and here there's a 0 here, here there's a 0 here. So this will be for these two, it will be 0. There's only a 1 here. So this value 3 will be taken. So after the convolution, your result will be 3. So you'll take this 3 and put it in this position basically. So what does that mean? You'll put this 3 is translated to this position, one position to the left. Similarly, this 3 will be translated to this position. This 4 will be translated to this, and so on. So basically, as we wanted, what we got is that every pixel that is present in this sense, they'll be shifted by one cell to the left. So that is how we achieve what we saw. So
Excuse me.
yeah, go on.
We will lose some of the pixels in the final image as well. If there is some kind of information in some leftmost pixel, we'll lose them.
Yeah. See, here, we voluntarily want to shift it to the left. It's not that you always have to do it. If you want to shift it to the left, definitely you will lose some information. So if you look at this, sorry, this was here. So if you look at this image, because some pixels got shifted to the left, see on the right, some of the pixels became white because there's nothing on it. So basically you have shifted everything to the left, so you have a bit of an empty space here. So it kind of, again, this the we wanted to show you an example as to what we can do with linear filters. So suppose if we want to shift it to the left, then this will be kind of a filter that does that. If you want to shift it to the right, then all you have to do is, instead of a 0 here, you'll have to put a 1, sorry, instead of a 1 here, you'll have to put the 1 here. Then it will shift everything to the kind of to the right. So this is application dependent. Even if we lose out, suppose these few pixels are lost, but that's what we wanted. We wanted to shift everything to the left. So we can't protect basically the images, the pixels that were there on the left, unless you do some kind of padding, and you want to make sure that you output an image that is bigger than the original image, such that it will not lose the leftmost pixels. So that is one way you
Uh,
can think.
padding
Sorry.
padding can
Yeah,
eliminate these losses.
that's what I said, that you can use padding that will increase your image size, but it will protect the leftmost
Yeah.
pixels. Yeah. So that's kind of, again, everything here, whatever you see, it's completely application dependent, so nothing has to be compulsory. So if you want to protect the left pixels, you will protect using padding, otherwise you'll leave them, you'll lose them, no problem. So again, I think I only have 15 minutes left for the coding part. So very very quick 1 minute, description. I mean discussion on this. So what is image thresholding? Uh, we want, this is a grayscale image. Grayscale means what? The values are between 0 and 255 pixel values. Now what we want is, we want to suppose convert it into an image where the pixel values are either 0 or 255, nothing in between. So that is done using this thing, image thresholding. So what we do is, we have a threshold defined, which is suppose 100 here. So if the original pixels intensities are greater than 100, then we'll put 255 here. Otherwise, we'll put 0. So here, whatever, I mean, these parts, they look brighter, right? So they definitely have intensities more than 100. So instead of putting that 100, we put a 255 here. So see, the face, the throat region, all these regions have turned white. Similarly, these background bright parts have turned white, whereas all the other parts which were darker already, they have turned black. So there's a lot of applications for it, but yeah, this is how image thresholding is done. So again, I mean, probably some older colleague of mine wanted to, I mean, asked you to work this out by yourself. So again, because of lack of time, even I can't go through it, but you can think of it like, uh, you know is this operation linear? So this is something that you can look at on your own time. So you'll study a little bit and think of it like, whether you can convert this into a linear filter, or is this a non-linear operation. So you can go through it on your own time, but instead of doing that, let's do something a little bit more interesting probably. So something that I think most of you will like. So this is the coding part. So basically here, what you learn is how to, whatever you are, so the fun with this kind of coding is that whatever you are learning in class as theory, you will get to implement them in the practical life. So um, I am assuming that some of you, maybe you don't know Python. So even if you don't know, there's nothing to worry about. Go through the tutorials that are available online. It's a very very simple language and coding language, and most of all, you'll enjoy it because it's so much like English. So it's nothing like, you have to learn big syntaxes and all. So very very simple lines, very very simple language and all. So here basically you have to first you know uh, import certain functionalities to basically read and write your image. So here what we'll try to do is, we'll try to look at the image. We'll try to, so previously, how do we look at an image? How have we looked at an image? We have taken some image file and used some Windows software or something like that, some image paint, anything, to open it and see how it looks like. So this is how we do it in the form of programming. So there's a library called matplotlib. Where is it? Yeah, yeah. So correct. So oops, sorry, I went to the wrong window again. Yeah. So this is where we'll learn how to basically read images. So you import some libraries that are required. So this matplotlib is a very good library for plotting, for basically plotting this. There's skimage, which is a very very image based library. So whatever image processing you want to do, you can do through this library. Somebody's I mean, please mute yourself if you are not talking.
Ma'am, excuse me, ma'am. Kindly zoom the screen, ma'am.
It's not visible,
It's not
is it?
visible.
Oh, is it?
Yes, ma'am. Kindly zoom the screen, ma'am.
Let me share it back. Is it visible now?
Yes, ma'am.
Cool.
Ma'am, it's visible, ma'am. Kindly zoom the screen
Zoom. I mean,
now.
it's actually
Just
okay.
confirm,
Okay.
please.
Okay. 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 So
Yes,
you,
ma'am.
yeah, it's better
Yeah,
now.
now it's okay.
Okay. Okay. Cool. Cool. Very good.
Yes,
So
yes,
yeah,
better.
yeah.
Thank you, thank you.
So basically, how do you read an image? You all you have to do is you use this import function. You import the functionalities that are there in this SK image library, and all you have to do is this io.imread. So whenever you are free, just try these things out. You'll have a lot of fun. So what you have to do? Let's try this out. Not okay. Anyway, so it'll take some time to run, but yeah, so all you have to do is write some code like this, which will this io.imread basically reads the images. So you give a path here, and that will read the image. Yeah. So now, once you have read the image, it's stored in this variable called img. And now what you can do is this matplotlib. This gives a very good, visualization tool for graphs and whatnot. So you can also, because images are also, you can think of them as matrices of size, some say suppose 512 cross 512, consisting of discrete values. So images also can be thought of graphs in some sense. I mean, they are similar in they are basically matrices. So you can use the same library to visualize the images as well. So this plot.imshow of image will basically give you uh, will basically do the visualization for you. So you can open images in this way also. So just try these things out on your own, and you'll have a lot of fun. So now, this IMG consists of a matrix of values from 0 to 255. So this PLT function has very beautifully shown this matrix as an image. But what if we look at the at the real values? So if you print this image, so in Python, so if you go through, you have to get used to this IPython notebook called Colab. So this is actually available with Google. So uh, yeah, I mean. So everything can be, it's like a notebook where you can add codes one by one in different cells, and it really helps if you use it. So if you print something like this img, you can see the values actually that are there. So all these values discretized between so you can see all the most many of the values that are between, obviously between 0 and 255. So that is there. And one thing you can note also is that, so how is this img, whatever it contains, this variable, what is it? It's basically a numpy array. So Python doesn't have the concept of arrays. So it only, if you know Python, you know that it knows lists basically. Yeah. So it knows lists basically. So to because we want images to be processed as, I mean, because these are matrices, we would like to have array and matrix functionalities in Python too. So that is given by this numpy library. So if you see this img, whatever this image, it's basically an array of type from numpy. So now this image, again you can see that this is a colored image. So that is why we know that colored images have three channels. So if you print the shape of it, so the shape means what? It's basically printing the dimensions of the image matrix. So you'll see that there's it's 827 cross 1241 cross 3. So this three basically stands for the different channels. So now there's another experiment. So again, this is fun to think of, that what happens if you use just one channel and don't use the others. So that is what is shown here. So this piece of code, it basically only prints one channel for you. So see here, it picks up the 0th channel, first channel and second channel. So the 0th channel RGB. So R stands for red, blue and green. So you can see that you have the red version, blue version and green version for the image. So similarly, you can you can so with these different these matplotlib or sk image, good things about, I mean fun things about these is that they can automatically convert a colored image to gray image to colored. Many functionalities are there, so you should go ahead and explore all of them. So similarly, one thing that you will often require to do in further assignments or whatever is that you may not always use the image as a matrix of discrete numbers from discrete integers from 0 to 255. It's often done. It's often seen to be. I mean, it's a good practice to basically normalize these values from 0 to 255 to 0 to 1. So that basically helps you in a lot of computations. So that is what they have shown here. So they have basically normalized everything from the range 0 to 1. And you can see that, yeah,
I have just a small question.
yeah,
So, as you just taught that histogram equalization, wherein the all the intensity in the matrix is basically in the discrete number, but you
hmm,
considered it to be a continuous
correct,
one
correct, yeah,
to get the better picture.
hmm.
So, that matrix equalization would be done before this normalization. No,
Yeah,
suppose if
yeah, yeah.
it is normalized, then it is already in the continuous. We can directly apply the
You
continuous
can say
function
it's
there.
continuous, but what are you doing when you are do so? Even though this looks to be continuous, this is actually not, because see, you have discrete integers from 0 to 255. You can't have anything more than that. So if you normalize, what will happen? You have 0 by 255, 1 by 255, 2 by 255. So it's
Yeah,
not
yeah.
that you have every value that is there in the real scale. So
Okay, okay,
you,
got it, got it,
yeah, yeah.
got it.
So this will,
Thank you.
even though this looks continuous, this is actually discrete.
Yes, yes. Thank you.
Yeah. So now this next again, so if you remember, we have converted the image now to grayscale. So now this image will be converted from, so since you have a grayscale, your third channel would be gone. So you only have one channel now. So that is why if you print its shape, you'll see that it's an 27 cross 1241 matrix. So no third channel is there. So similarly, you can there are some other tools which you can again examine later on your own time. So so this SK image is actually a very powerful tool, and you can generate images from it. So if you, for example, here we have generated an image of a horse. So all you had to do was do this skimage.data.horse. So they have some images already predefined. So uh, so similar. I mean, if you plot this image, it becomes like this. It looks like a horse. It's a horse image. So yeah, I mean you can utilize these functionalities as and when required. And similarly, you can see that this looks like a binary image, grayscale basically. So because of that, it won't have all the three channels. It only has one channel. So one thing that we talked about binary images just now, where here we showed that what happens when we do image thresholding on a grayscale image. So suppose you have a binary image like this. So as I said that this is black and white, so this looks like binary. So if you print this image, you'll notice that instead of numbers, it's only true and false. Why? Because true stands for, suppose true stands for 1, and you only have two values, right? So 0 and 1. So you can think of 1 as true, 0 as false. If you do that, then you can store, basically instead of storing the integer values, you can store the boolean values, which are better in terms of storage. So it's already written here. So you can that is how NumPy stores binary images to constrain the sizes. So yeah, let's keep these parts. So yeah, so there are many more examples which will help you basically to um, you know there are different functionalities that are performed here, some different transformations. Let's look at the results first. So there's this original image. So there's this transformation basically increase the intensity, right? So because what did you do? You had an image, you added 40 to it. So every pixel is summed by a value, increases by value 40. So naturally what you see here is a brighter version of this image. Similarly, you what you can do is, here they say that you flip the rows. So in once you go through Python in a better way, you'll understand how flipping rows and columns happen. But basically, what this means is that you have basically inverted the image. So the row here comes here, then the second row here comes here, and so on until the last row here comes here. So basically, you have inverted the image. And similarly, you can flip the column, which means that this person will be looking in this direction. So it'll be turned on the vertical scale. So these interesting things you can try out. Again, these are kind of at this point very Python type of skills are required to do these functionalities. So I think these will be easier for you if you understand, if you start looking at the image from a matrix perspective, and you try to learn how to manipulate matrices in NumPy. So then you'll be able to do these by yourself. But yeah, please play around with these things. Yeah, so I think it's already 7, so it's better that we stop here and we'll continue with the rest of it. A little bit is left. So yeah, we'll end here today because the time is up. Yeah, so we'll show the other things in the next session. So there are a couple of more interesting pieces to cover. Yeah,
Can you please share the notebook?
yeah. I'll talk to the other TAs about that, and I'll see if, how to share this with all of you. Thank
Ma'am,
you,
thank you,
everyone.
ma'am.
Thank you.
Thank you.
Thank you for Lucan. Thank you very
Thank
much.
you. Thank you.
Thank you.